Well, thank you very much for your invitation and for your hospitality. I've enjoyed Ljubljana very much so far. And this is special for me because I'm Canadian originally, and my very first job was working for the Geological Survey of Canada. So it's nice to be in a geological survey again. So thank you very much. So I'm very grateful to the European Association of Geochemistry for naming me their distinguished lecturer for 2019. I didn't actually know anything about the program until they told me, and it seems like a very good program for me to meet all of you, and hopefully for you to listen to what I have to say today. So the EAG asked me to let you know a little bit more about them. There's a lot of support for early career scientists, and I see there's a lot of you in the room today. There's a sponsorship program for students, early career ambassador program, and lots of job opportunities. So please have a look at the EAG website. They're very active now, and there's lots of opportunities with them. And also they have a very nice journal, the Geochemical Perspectives Letter. It's open access, so everything's out in the world, no page charges, and articles that aren't too long, so 3,000 words isn't too bad, and it's a community journal, so there's all sorts of aspects about geochemistry. So please look them up. They're a very good organization, and again, I'm very grateful to them for being here today. So I have 3 lectures for you today, so it's very exciting to see so many of you here. I'm going to do 2 of them, and then we'll have a coffee break, and then we'll come back for the 3rd. So we'll have a little break, and there'll be a break between the 1st and the 2nd lecture. So the first lecture, I'm going to talk to you about one of my favorite things, which is a bit odd, and it's mine tailings. And the title is really about what I'm going to tell you about tailings. So what are they? Where do they occur, and where do we get rid of them? How do we study them, and why are they important? So these are some mine tailings from my home country of northern Canada, and it's very typical tailings, and we're going to be looking at those in a lot more detail. Okay, so let's start out thinking about what are tailings in the first place. Why are they so interesting? So by definition, they're mixtures of the crushed rock and the fluids that are used to process the ores once they've been through the mills and the washeries or the concentrators, if you're gravity concentrating. So after you've taken out the really economic materials, your gold and your silver, this is the waste material that's left over. And it can be tailings from the extraction of gold or copper. So the tailings on the far, I've got a pointer. The tailings on the far right are from Northern Ontario. That was a copper and I think a gold mine as well. Unfortunately, some of these tailings that contain sulfides can generate acid mine drainage, which I'll mention a bit later. And you can have tailings that are red as well. These are tailings from aluminium processing. So tailings come in all sorts of colors, but one thing that's very common to them is they're all very fine-grained. So they're all really ground up. And that creates some problems with them that we'll discuss a little bit later. Okay, so tailings, as I said, are made up of minerals and fluids. So actually, as geologists, we're really well placed to study tailings because we know how to study minerals. So I'm actually a geologist by training. I trained as a geologist in Canada, and I worked in mineral exploration for many years before moving to England and becoming an environmental scientist. So having a good geology background was really good because it means we can study these minerals and fluids in tailings. So this is an example of sulfide tailings, and I've tried to just break up what the minerals are. So mainly it's the minerals that contain the economic materials that have been extracted. So these sulfide tailings have lots of sulfide minerals. Things like copper are very economic in some places, galena and so on. And so the processing of the ores is generally not 100% efficient, unfortunately. So we often end up with small amounts of the tailings that contain these metals. Unfortunately, we also end up with things that are toxic. So arsenopyrite contains arsenic, and of course we know that's very toxic to organisms and to us as well. But these days we're looking at tailings for potentially reprocessing. So all of these things in red could be economic today, and I'll come back to that later. The other thing we have are the processing fluids. We have other minerals that sometimes we forget about. So the carbonates, the silicates, the minerals that are not economic. But actually when we're studying tailings, it's very important for us to know about these minerals because the tailings sulfides, in this case, can react with these minerals. And with sulfide tailings, this can lower the acidity. So when we're studying tailings, we try to look at everything that we can, ideally. So as I said, tailings mineralogy is one of the things I find very interesting. And to understand how tailings behave in the environment, it's really important for us to understand the minerals in the tailings. So I've got a couple of examples here. The pyrite-rich tailings on your left are from Bolivia. One of my PhD students was up studying those. And the picture there is a bit odd. It's from a QEM scan. So that's an automated mineralogy microscope. And so instead of you counting each grain, the microscope will count the grains for you and decide what minerals they are. So it's very nice, and it takes a lot of work away that we might have to do. And in this picture, actually, the pyrite is purple. So most of the material in this is pyrite. And pyrite, unfortunately, is something we don't want getting into the surface environment because it reacts very well with oxygen and water and bacteria, and it can generate acid mine drainage. So these tailings, because we know there's so much pyrite here, we can predict how much acid mine drainage might be forming. But not all tailings have pyrite, and not all tailings are very toxic either. These are some tailings from Mount Polley, and I'm going to talk about the Mount Polley tailings dam spill in Canada. And actually, it's difficult for you to see these minerals, but they're mostly minerals, metamorphic minerals, from high-grade metamorphic rocks. And so they're pretty benign, they don't contain a lot of pyrite. And so although we often think of tailings as toxic, and you often hear the news reports saying, oh, these terrible tailings, often they're not very toxic. And again, that's important for us to understand, so we can plan remediation if we need to. But there are some tailings that are toxic, there's no question about that. So here's some sulfide tailings from different areas, from Bolivian in Sweden, from Potosi in the very high parts of Bolivia, and from Portugal. And just for comparison, I've included the Dutch soil remediation target. There are a number of different targets people use. Often they're country specific and specific to the background. So these are quite low values. We don't want a lot of the arsenic and copper and lead and zinc in our soils. But you can see that these sulfides all contain very high concentrations of these elements. And so these are potentially toxic elements. And again, it's important for us to know if these elements are in our tailings so that we can remediate the tailings if necessary. So we don't let these elements go into the natural environment. So we use a lot of geochemistry and a lot of mineralogy to study tailings. And as geologists, it's perfect for us to do that. Okay, so where are tailings stored? So tailings are a huge volume, I'm sure you know, a huge volume of mine waste generated. If you think about ores, in the old days, ores may have been maybe 10% silver or very high grade. These days, we've taken all the high ores away, and the grades of ores are very low. So maybe 0.3% copper, less than 1% copper. So there's an awful lot of waste, if you think about it, generated all the time. And tailings is one of those wastes. So there are many ways that tailings have been disposed of, both in the past and today. So rivers are one of the main places tailings end up. In the past, there wasn't much environmental legislation, so the rivers were convenient. You could throw the tailings in the river, and they would go away, and you didn't have to worry about them. So that is an old thing. It still happens today, unfortunately. Also in oceans, so here's submarine disposal in Langfjorden in Norway. The ocean, again, seen as a good dumping ground for tailings. But more managed tailings are things that mining companies are working towards. So using them as backfill in the underground pits, maybe cementing them with a binder and using them as backfill is very popular. Dry stacking like this is becoming very popular, especially with tailings dam failures happening. So the idea is that you dry out the tailings, you take the water out, and you stack them in a dry environment. And it works very well if you live in an arid environment like you see here, but maybe not so well in a wet environment. But it's becoming much, much more popular, dry stacking. The main way that tailings are stored is behind dammed impoundments. So here are some examples of that. We've got different types of tailings. This is in northern Canada in Saskatchewan. It's a uranium tailings dam. This one you've seen in northern Ontario. It's a sulfide tailings. And this is an aluminium bauxite tailings repository. So all looking quite different, but stored in the same way. So the idea is you have an area that you can put the tailings in, you pipe them in. They're a mixture of fluid and minerals, and then you keep them covered with a cap of water, like you see here in all the cases. And the water is meant to keep the dust down. You don't want them turning into dust. And it also prevents these sulfides from oxidizing. That's what you don't want as well. So this is the most popular way, and it has been done for many, couple of hundred years at least. And there are different ways that tailings dam can be constructed. These are just some cartoon examples. So generally, you've got the tailings in this part, and this is the wall, this is the dam. And the dam is often made of local materials. Obviously, that's much easier to get local materials, it's cheaper, and sometimes it's actually made of the waste rock and tailings themselves. So the idea is you start, in all cases, with the lowermost bench, and then as you mine and you make more tailings, you keep adding benches until your tailings dam gets fuller and fuller. So the most popular way is this upstream method. It's the easiest way to construct, and you can just sort of keep constructing on top and filling up your tailings dam. But unfortunately, it's the upstream tailings dams that tend to fail and tend to cause big accidents. And the most recent dam failures in Brazil, there was one in 2015 and one this year in January, were upstream tailings dams. And Brazil and a lot of other countries have realized that these are not good constructions, and they're going to start decommissioning these in 2021. But we're still left with a legacy of some of these upstream dams. So you can see examples of good and poor practice here, and it all has to do with where the water table is in your tailings facility. So this line shows you where the water table is. Poor practice is where the water table lies close to the dam wall. And the reason that's not very good is that that water and the pile of tailings puts a lot of pressure on the wall. And that causes instability in that wall, and the wall can fail. Better practice is where you have a very thick wall and you have your water table set far back. So the wall has a lot of strength and hasn't got that pressure from all that water and all that tailings. So there's a lot of recognition going on about tailings dam construction now with these accidents that have happened, and people are moving towards better practice, which is good news globally. So let's ask the how question. How do tailings impact on the environment? Well, the main way is that these tailings dam failures that we hear about. There is another way where tailings are just dumped in rivers sort of continuously, but the more spectacular accidents and the ones that kill people are these tailings dam failures. So there is compilations and people collecting data on tailings dam failures around the world. And we recognize that since the early 1960s, there have been about 110 tailings dam failures. But unfortunately, that number is probably far, far too low. There are many countries that don't report the tailings dam failures. Sometimes mining companies don't want to admit to them. And some of the older tailings dam failures, the records have been lost. So that number is a very minimal number. But we know that the effects can be devastating. So we know there are damage to ecosystems. When the tailings come through, they generally kill everything in their path. And because of the long-term effects on the river systems, the ecosystems sometimes take a long time to recover. Communities, so human communities along the river, we know there have been deaths from these tailings dam failures. Communities are affected by the deposited tailings. And again, there are short-term and even longer-term impacts. That figure is the figure that is in the compilation, so people killed by tailings dam failures. And again, I would imagine that's quite an underestimate because we don't have the records. And of course then, if remediation does take place, it doesn't always take place, but when it does, it's very, very expensive. So it's expensive for the mining companies to do that, and it does damage the reputation of mining. People see these things and they think, oh, mining is terrible, we mustn't do mining. And, well, I'm going to talk in my next talk, I think we need mining. So it's not very good for mining reputation. So there are a lot of issues with these tailings dam failures. This is a picture of a failure in Mount Polley in Canada, in British Columbia in Canada in 2014. I'll talk about that a little bit more. I've worked on that one. And this is the one in Hungary in 2010. It was a bauxite aluminium processing failure, and it's very red mud that you can see there. But there are a number of examples. So if you're interested in tailings dam failures, there's a very good website. It's the WISE uranium website. I'm not sure why it's uranium, but they're doing a great job of compiling information about tailings dam failures. So this is just some examples from their database to show you some of the features of tailings dam failures. So the first one is whether they're active, i.e. are they still receiving tailings, or whether they're old and have been abandoned. And I know I haven't got a very big data set here, But in fact, most of the dams that fail are active. So that means they're ones that are receiving tailings all the time, and you've got a lot of very wet material. It's sort of unconsolidated, and sometimes mining companies might put a little bit too much material in the tailings dam, and that causes problems. The inactive dams tend not to fail so much. And there are many reasons for that, but one of them is when they are allowed to sort of sit, they actually form some mineral cements in the tailings, and that provides stability for the tailings. So actually that natural process of cementing prevents the tailings dam failure. But it doesn't always. There are some inactive ones that fail. The other thing to notice is the reasons for the tailings dam failure. And it's important to know this for companies because they want to prevent these things happening. So some of them are natural events. Here we've got earthquakes that cause the instability of the dams. Poor maintenance is very common. So once you build the dam, you have to keep maintaining it. You have to keep checking it to see if there's any leaks. Often there's a problem on where you build the tailings dam. So if you build it on material that's unstable, like clay material, or in the case of the Canada tailings dam spill, there was a layer, very deep layer of glacial clay, and that provided enough instability that the whole dam failed. So it's really important to know what's actually underneath. And then again, the wall, so that dam wall can fail as well. So knowing the materials in there, whether they're going to be stable over the long term. So there's lots of reasons, unfortunately, why these dams fail. So ever since I worked in the environment, I've been really lucky, and I'm sure a lot of you are, to work with people from different disciplines. So I've worked with microbiologists, engineers, social scientists, and when I started out, I started working with a geomorphologist, so a physical geographer. And that's been a really good collaboration because I work on me and my students work on the geochemistry and the mineralogy, and the geomorphologists look at the morphology of river systems and how they respond to environmental change, and in this case, tailings dam failures. So we've recognized that actually after tailings dam failures, it's the rivers that are most impacted. The tailings dams are often built in high ground. When they fail, the material flows out, as you can see here, along river systems. So it's everything in that river system that's really affected by the tailings dam failure. They experience erosion. When this material goes through, it can take out all the sediment or rock that was there before. If there's alluvium, so sediment in the river that's already contaminated, that can be moved around and cause problems. We can also see tailings deposited in very thick layers over the floodplain, like you can see here in Kolantar. If there's toxic elements in the tailings, then that can affect the soils and the people and the ecosystems, and there may be health impacts as well. So for 21 years, we've been studying the after effects of these tailings dam failures, but not only the failure, but also whatever remediation was happening as well. Because sometimes remediation takes place, and sometimes it doesn't. So with that work, we've tried also to put together global ideas, trying to think very globally now, of the global impacts of tailings and tailings dam failures. So you'll see this again a little bit later in a different color. But what you can see is we have very good data for certain parts of the world. So we have good data for the US and Canada, Chile, Australia, parts of Asia and Europe. But there are many areas of the world where either the data don't exist, maybe Africa, or in China it's actually very difficult to get a hold of the data, and we haven't got anything from Russia either. So it's a start, and we're hoping to build up this database. There's a lot of data that's freely available. I know that you have data here in Slovenia that's freely available, and it's really useful for doing these global compilations. So it's useful for us because we can see where the tailings dams are, and we can see where the big failures have occurred. And there's not really much pattern yet that we can see, apart from the fact that we are seeing these larger tailings dam failures. These are the ones in Brazil. These are ones in Papua New Guinea, I believe, and one down here, and of course the one in Canada. So starting to get a picture of where the failures might be, and then using this spatial information to help people in these areas. So if you're in an area like Mount Polley, you need to know what the people are in that area, how many people are going to be affected, are the ecosystems going to be affected? So we're still working on this, and hopefully we can build it up as well. So the other thing we've done is go to certain areas and study these areas as a case study. So I'm just going to show you a few of these. So I'm taking you now to New Zealand, and this is actually a tailings dam spill that happened in 1907, believe it or not. So in 1907, there was a gold rush in New Zealand, like many gold rushes around the world, and they mined gold that was associated with arsenic. That's very common. And they had it in a dam, and unfortunately that dam failed. And actually you can see, this is an old picture from that time. This is all the material, and it was a tourist site. So these lovely ladies are out in their nice Sunday dresses going to visit the tailings dam spill. And so it caused some problems, it killed cattle, and at the time it was quite a big problem. So we went and we put some cores into the floodplain, and we were able to map this yellow zone, and it actually is yellow. So it was really easy to find. And we can see that the effects of that tailings dam spill are now buried in that floodplain. So there's about 1 meter or 2 meters above all this material. So this is actually looking at a layer below the ground. So we can get an idea of the volume of that spill and how it might have affected the area. And we can say something about what its environmental impact could be now. So because it's buried, I think it's fine. If it stays buried, it's not going to cause too much problems with groundwater. The arsenic concentrations aren't very high. So I think as long as it's buried, it should be fine. If, however, more development goes on and some of the floodplain is dug up, they're going to need to think about this as a contaminated layer. So that's a historic example, and showing that these sort of things were happening in a small scale at that time. If I take you to Spain in 1998, this is the first one I worked on. You might remember this, some of you might remember this spill. So this is the Guadiamar in southwest Spain, in the Iberian Pyrite Belt, a very famous area for copper, zinc, massive sulfide deposits. The mine is up here, and there's the tailings dam. So this is the Rio Guadiamar, very nice area, lots of nice houses and orange trees and so on. And overnight, that dam failed. It was built on clay, and that clay, well, during the summer months it dried out, so it shrunk. During the winter months it swelled because it took in water. And many years of that caused the dam to fail. So you can see that the dam, the material in the highlands was confined to the valley, and in the lowlands it spread out quite rapidly. So this was very big news in 1998. There hadn't been a dam spill like this for quite some time. It made a lot of headlines. And the big worry that was down here, there's a place called the Doñana National Park. And that's an area where birds coming from England and Northern Europe would stop on the way to Africa as they migrate. So there was a lot of concern about that park. So they did a good job, really good job of remediating this area. The government and the mining company got together the next day, and they made a plan, and they put up a wall here to stop the flow of the tailings getting further. So that stopped big problems in the park. That was a really sensible thing to do. Just a wall, and it really worked very well. The other thing they did was to go and get big teams with shovels and trucks, and they got out on the floodplain and they dug up all of the tailings. And sometimes it was up to 4 meters thick of tailings. So that took from April to December to dig up all this material and drive it back and put it in the open pit. So it was a really big accident. So we worked on several aspects of that. So this picture is now, what is it? Where do we go? I think it's either December or January after the spill. And you can see they have cleaned up, so there have been trucks driving around, but there's no vegetation left except for the trees. They had to remove the vegetation to get all the tailings. So in terms of getting the tailings and all the contaminants, like the arsenic and copper, they did a great job. Only thing they could have done. But in terms of the geomorphology, by taking away the vegetation, the river morphology then changed and responded. And unfortunately, they had a period where there were a lot of intense floods afterwards. So here's January 1999, after the spill. The river is very sort of at equilibrium. But because it was all loosened material now, without any vegetation, it responded. So there's a lot of deposition, and the channel moved. and the channel widened at times, and it took about 10 years for it to re-equilibrate. So it's an interesting case study. On one hand, they cleaned the tailings, they had to do that, but they changed the geomorphology. So it always has, there's no perfect system. You have to balance the best thing and to lower the risk to people. The other thing that was interesting was, this happens in a lot of situations throughout the world, because we've had historic mining as well. So we know there's been historic mining, and that has left contaminants deeper in the floodplain. So this was some work showing that when we put cores in, although they took the top layer of tailings, there was older tailings before 1954 that were still contaminated in the floodplain. And because of these big floods, some of this material was moved around as well. So there was about 10-year period of instability following this tailings dam spill. But the good news is, this is from 1999 to 2002, overall the concentrations of metals, zinc, lead, and so on, declined in the system. So there was a big pulse at the beginning, you wouldn't want to drink the water, but over time it settled down. So the systems have a good way of self-regulating themselves. That's really important to remember. So if we go to Brazil, this is the one that happened earlier this year. By the volume, it wasn't one of the biggest ones, 12 million cubic meters. But in terms of the human side, I think it's one of the most devastating tailings dam spills. So it's an iron ore mine, so actually the tailings are not very toxic. You might hear reports that they're very, very toxic. I don't think they are. There may be a little bit of chromium and a little bit of arsenic, but it's mostly iron. The main effect is the volume of material, so it's swamping the river, and the fact that it killed so many people. So it went through the lunch place and just killed so many people. At least 207, probably 300 people were killed. Very devastating. The company is starting to clean up, and again, the cost could be billions and billions of dollars, because these are very large systems, and hopefully they will compensate the town. That's a bit up in the air at the moment. Just have a bit of water. Okay, so that's the sort of very bad side about tailings and good side, but so why should we think about tailings? Why should we research tailings and tailings dam failures? Well, I think the first thing that we can contribute to is understanding, so it's a lot of words, understanding how these contaminants, how these toxins might be released once tailings get into the environment. So because we're geologists and geochemists, we can do these studies, and that will help to design management schemes and remediation schemes. If we can understand, are the contaminants going to move or are they not going to move? That really helps. So I'll take you back to Bolivia now. This is the Rio Pilcomayo that we've studied for about 20 years. And this is the Cerro Rico de Potosí. So it's a rather magnificent mountain at about 4,500 meters above sea level in Bolivia. And it's a mountain full of tin, silver, lead, zinc veins. It's very, very rich, or at least it was. So before 1540, the indigenous peoples didn't mine the mountain. They thought it was holy, sacred. They left it alone. When the Spanish came in 1540, they thought, oh, there's lots of silver in that mountain. Fantastic. Let's get in there and mine it. So they mined it like crazy, and they mined, it's like Swiss cheese now. And it was the basis for their empire from 1540 onwards. To get the silver out, they used a lot of mercury, which probably came from Slovenia at that time and even since, to amalgamate the silver. And so the wastes here, the veins are very interesting from the economic point of view, but the wastes are very toxic. So there's a lot of mercury in the waste, there's arsenic, antimony, thallium, almost every element under the sun. So this is the town of Potosí. It's the mining town. Even when I went there in 1998, there were still miners who were working small scale, and they would get up and walk up the mining shopping street. They would buy a candle for their helmet. They would buy coca leaves to chew for the altitude, and they would buy alcohol to give to the goddess of the mountain so they didn't get killed. So you can go here and you can actually go and mine tours. It's fascinating to see how it works. But we've been studying the Pilcomayo. So the Pilcomayo is a very large river starting at this area in the high Andes and going downstream through Bolivia into Paraguay, and it actually comes out at Argentina. So it's a very long river system. And like a lot of river systems around the world, it has gotten tailings a lot. So they've constructed tailings dams in the last 10 years, but before there was nothing. So all of the tailings were discharged to the river, all of them. So we've been able to find evidence that it goes at least down here to Villamontes, which is about 500 kilometers downstream. So the whole of the Pilcomayo has mine tailings in it. So this is what it looks like. It's a fantastic river. It's a beautiful area, but it's rather odd because this is a dry season in 1998. You can see that the river is gray. That's a bit odd. Gray rivers are uncommon. And the reason it's gray is the only thing that's in it is mine tailings at that time. In the wet season, it's a normal river. So it's full of gray tailings, and the floodplain is pink, which again is rather odd, but that's because these tailings will then oxidize in the floodplain. So we know there's a lot of material in this river. So we don't know how deep that is, but it could be quite deep. It's a big Andean river system. So we've done a number of studies, and one of the more recent ones we did was to look at indigenous villages. So these are villages along the Pilcomayo, and you can see they have agricultural areas. They grow crops for themselves and for some of the larger areas. Here they are growing some crops. So we were interested to see, is there any impact of the tailings and on the crops that they grow? So they luckily don't irrigate the fields with any water here. They know that water is very bad. They get it from the mountains. But occasionally the tailings will get deposited on these fields. So they are contaminated. We did a study on some of the crops, and fortunately they were mostly fine. The only thing that had high things like cadmium were lettuce. So anything leafy that they wouldn't wash had some contaminants. But most things were fine. That's great news. So I had a student, David, who did a PhD when I was in London, University of London. And he did a 3-year experiment using mine tailings and soil from the floodplain. And what he was trying to do was understand how did the tailings react if they were on their own with soil or in a simulated tailings dam failure where you have a layer on top. How did they weather? How were these elements released? Would that have impacts on some of the poor waters and vegetables? So he made his columns that you can see there. He filled them with these materials. And then he conducted experiments where for 3 weeks he would put water on the columns. That was the wet season. For 3 weeks he would dry them out, and that was the dry season. He collected the water at the bottom, and then he studied the geochemistry of the water and also the geochemistry of the tailings before and after the experiments. So I won't go into too much detail, but just to say, so he did it for 20 of these years, over 3 years. So it's a long time to do experiments, but he got some very nice data. So I'll just show you a little bit about zinc and cadmium. Now, if you remember your periodic table, zinc and cadmium are in the same column of the periodic table, and they normally behave in a similar way. They have the same atomic radius, atomic size, and they both form 2+ cations. So normally we see similar behavior. But you can see from this, if that's true, the line should have been flat. But you can see it's kind of not, all over the place. And cadmium is much more toxic than zinc, so we were quite interested in this behavior. Why was this happening? So he went to the minerals, and he found one of the reasons was this mineral. So this is they're zinc sulfide minerals. These are a microscope we use that can map the chemicals in minerals. So this is all zinc, and this is all sulfur, so it's a zinc sulfur grain. You can see the cadmium here is more concentrated. The lighter color is cadmium. So there's lots of cadmium here and no cadmium here, and no iron here and lots of iron here. So what he actually found is there are two minerals of zinc and sulfur. There's one called wurtzite, that contains the cadmium, and there's one called sphalerite, and that contains the zinc. Wurtzite is much more unstable than sphalerite, so it will dissolve first. And that's why we see cadmium coming out in the pore waters before zinc. So the cadmium is coming out of the wurtzite. So that was one piece of the puzzle. And the next slide shows you how difficult it can be to work on natural samples. So it's quite complicated, but what this is showing you, here's our plot. And this is sort of a summary of all of the processes going on all at the same time that explain these ratios. So here's the zinc sulfide, the wurtzite weathers first, and then the sphalerite. But at the same time, we have secondary minerals, rust iron forming. Sometimes they take up zinc, and sometimes they release it. We've also got other sulfate minerals that form during the dry season and then dissolve in the wet season. And then, of course, we mustn't forget, in the soils, we've got organic matter, and that plays a role as well. So picking apart all these natural processes, all going on at the same time, is complicated. But I think we have the tools to do that. And then the main message is that over the 20 years, a lot of the cadmium was leached out. So in this one in particular, 100% of the cadmium was leached. Now, lab experiments are much faster than the natural world. So that's probably an overestimate, but it just shows that the cadmium is very mobile. And so we've tried to talk to the people to grow crops that were not taking up cadmium in this particular case. Okay, so let me take you now to Canada. So this is the Mount Polley spill. This is in 2014. At the time, it was the largest tailings spill ever. It's been superseded by one in Brazil. So this is what it looked like before, and this is what it looked like afterwards. So the tailings dam here failed because there was a layer of glacial clay underneath that was unstable. The material flowed out very quickly. It flowed here and got stopped by this lake. So then it turned and went through this creek into this lake. This creek, Hazeltine Creek, used to be 1 meter wide. After the tailings dam spill, it was 150 meters wide. That's how much material went through. It scoured out everything in its path and then dumped all the material here. You can see a little bit of turbidity here. There was a lot of concern for many reasons. One is that this lake is a major area where salmon in British Columbia come to lay their eggs. And so the people were very worried about this spill having a big effect. We won't really know the effects of that until probably now, because it takes 5 years for the salmon to go through the cycle. So there are biologists studying that. The other issue is this area is populated by indigenous Canadians who've lived here for thousands of years. And they look at the land in a lot different way than we do. To them, the land is part of them. And they felt that they had been violated, that they had been hurt by this accident. So the mining company did a lot of effort to try and talk to the local communities, and a lot of effort to try and do some right things for this area. So they cleaned up a lot of the debris, the trees, and then they got engineers in and they built a new channel like this. They put a pond here to trap sediment going into the lake, and then they tried to grow vegetation. And luckily, the vegetation that's 5 years now is growing. That's good. And they have been lucky in that they haven't had any big floods. So the channel is still there, and it hasn't been moved. So they've done a really good job, I think, in trying to do what they can do. It's cost them a lot of money, about 70 million Canadian dollars so far. So that's a lot. So our team of geomorphologists and geochemists and mineralogists went here. And the geomorphologists are working on their predictions, and we've done some work on the tailings. So the tailings are not very toxic. That's really good news. There's a little bit of copper because it was a copper mine, and there's a little bit of vanadium that's probably in slight excess. So one of my colleagues worked on the copper, and I worked on the vanadium. So these are you've seen these tailings before. These are the gray tailings with mostly magnetite, and these are red tailings with these metamorphic minerals. So the vanadium concentrations are the guideline is about 200 milligrams per kilogram. Sorry. So they're not very high, but they're high enough that we wanted to study them to see if it was going to cause a problem. So we went out in 2015. The geomorphologists did some drone surveys, so they're looking at the river morphology and how that's changed. We sampled the waters and the tailings, and actually we noticed these pools forming from underneath the tailings. These contain iron oxides, new iron oxides, and so we were quite suspicious that maybe there's been some mobility of vanadium here, so we sampled those as well. We looked at the water concentrations, and you can see before the spill the concentrations were about 1. After the spill they had increased to about 10. That's still well below guidelines, so it's 50. So the water seems to be okay, which is fantastic. The water, however, in those pools that you just saw with the iron is a little bit higher. So there is some vanadium mobility under those pools. We then used our tools of mineralogy again, and we went to our synchrotron in Canada, in England, and we were able to look at whether the vanadium was vanadium 3+ or vanadium 5+. So what we found is that there was vanadium in the original minerals, titanite, which is a silicate, and magnetite, which is an manganese oxide. And that was in the original tailings. In these secondary minerals, there was vanadium with those, here it is, and it was in the form of vanadium 5. So that's the mineral side. Then my colleague Patrick, who you can see here, put some cores down into the floodplain, or into the channel, and we looked at the water with depth. So the water in the stream was very fine. It was about 10 micrograms per liter of vanadium. That's very good. However, when you get below the interface between the water and the sediment, the concentrations just go up. So you go from 10 to 2,000. So there's a reaction going on below that front. A huge reaction. Most of the elements follow that. So we put together a model to try and explain this, and then to think about vanadium in the future, and is that going to be causing a problem in this area? So here's the cartoon. So what we think happened is the tailings were deposited. Here's the magnetite and the titanite. They contained vanadium 3+ and a little bit of vanadium 4. Below that sediment water interface, they undergo dissolution, probably reductive dissolution, probably with bacteria, we don't know, but the vanadium is released. It then oxidizes to vanadium 5+, and that diffuses upwards. But the great news for the mining company is that vanadium 5 is then taken up into these secondary minerals. And so that's what keeps the concentrations low. So it's a natural process, purely natural. The only unnatural thing is the fact that the tailings were deposited. So this is an example of natural attenuation. It's good news for the mining company. Overall, the concentrations will be kept low. These concentrations here are quite high, but hopefully that won't affect anybody. Okay, so that's the first thing, understanding the contaminants. The second thing is we want to help mining companies, if tailings dam failures happen, to design methods to figure out what they should do. Should they clean up the tailings? What should they do? So there's lots of outstanding issues. The response to tailings dam failures is really variable. Sometimes there's cleanup, sometimes there isn't. If there's good laws and social pressure, people will clean things up. It takes money, but they have to do it. Sometimes nothing is done. The remediation is extremely costly. Millions to billions of pounds or dollars. It takes about 1 in 5 years, and it sometimes isn't completely effective. So it's very costly for the mining companies. And even if remediation is carried out, the natural attenuation is still required and does take place. So we put together some models, little cartoons, to try and figure out what we could tell mining companies to do from the geomorphology point of view and the geochemistry point of view. So this is time on the x-axis. So this when man first appeared, and women, of course, men and women, decided they didn't need too much mining, so there wasn't much contamination at that time. In the Industrial Revolution, the contamination from mining went up because there was a lot more mining and a lot more pollution. That Industrial Revolution sort of tailed off in the early 1920s, but there's still contamination. When a tailings dam failure comes along, boom, there's a lot of contamination and a lot of change, in this case, in the floodplain. Here are the various options. If you re-engineer the channel, like at Mount Polley, that will do something for a while, but if you have a long period of flooding, it'll change the channel again and you'll still need natural attenuation. If you remove the tailings, the same thing will probably happen, but natural attenuation will be needed. If you use chemical treatment, that won't have any effect on the geomorphology. The geochemistry side is the same at the beginning, but it's slightly different here. If you remove the tailings for the geochemistry, that's fantastic. That's what you should do, because you're taking away the contaminants. If you chemically treat, like they did in Hungary for the red mud spill, that reduces the contaminants as well. If you change the channel, that won't do anything for the contaminants. Again, natural attenuation is required. So we have these ideas about how long things take and what you should do, but we're writing a grant at the moment, I hope, I have some time, to try and answer these research questions. There's too much words, but basically, can we decide which, for any given river system, which is the best practice? Should we put a new channel in, or should we just clean up the tailings, or should we just leave it? That's a difficult one to do for natural attenuation. What should we do? What should we recommend? So we're going now to try and look at write the grant and go and look at some other tailings dam spills that we haven't studied to get a broader picture, and hopefully we can help companies and governments as well to figure out these answers. Okay, so that's a lot about tailings. So what are tailings? They're mine waste of the crushed rock and the processing fluids. Where are they disposed of? All over the place, but mostly in dammed impoundments. Unfortunately, these can fail. How do they impact on the environment? They can contaminate soil, water, they can produce dust, they can affect health. Why should we care? Why should we do research? We can help to understand how the contaminants move, so we can help design remediation schemes, and so we can reduce these negative effects. That's what we're trying to do, trying to protect the environment and promote safe mining. That's what we're all about. Okay, thank you. That's the first one.